So thank you very much for being here. My name is Ceren. I hope this is not too loud, okay? I'm an ITAM fellow at Harvard, and ITAM stands for Institute for Theoretical Atomic, Molecular, and Optical Physics. And I'll tell you about how we can break ergodicity, in particular, in the context of connections between quantum scars, quantum many-body scars, and regular states. So I made that clear, that distinction, quantum scar and quantum many-body scar, and it's going to be more clear in a second. So this is a work, a postdoctoral collaboration with Bertrand Everard from ETH, Andrea Pizzi, and Simos Mistakidis from Harvard. Okay, so for most of this talk, I'll be focusing on our existing work here, because that is really in the spirit of this conference. It has all-to-all interactions. But at the end of it, hopefully for 5 minutes or so, I'm going to tell you what we're up to now, going from this direction. Okay, and then this talk is about cold atoms. And cold atoms, as you know, is part of what's now called quantum synthetic matter, and among many other hardware. And these systems are called quantum synthetic matter because we basically use these systems to quantum simulate the fundamental principles of physics in the laboratory with high control. There are many examples of quantum simulation experiments now in the literature, but I'll just point out a few very relevant experiments to this talk, in particular in the context of thermalization and related topics. So for example, the measurement of entanglement entropy, and to probe the closed system thermalizations and optical lattices. Closed system thermalization is a topic that was discussed by by Mark, and then before by Marcos. And measurement of MBL or pre-thermal MBL phase, and again in optical lattices in block experiment, and perhaps a little bit changing the hardware. Measurement of dynamical quantum phase transitions in Chris Monroe group and ion traps. We actually heard about the latest developments in this direction from Guido earlier in the conference. And maybe the spatio-temporal spread of spatio-temporal correlations in a superconducting quantum processors in Jwei Pan group in China. But perhaps one of the most a hardware that got lots of attentions in the recent years is Rydberg atom arrays. So you already know what a Rydberg atom array is. I don't need to give an introduction thanks to Misha, but it is basically an array of atoms that are excited to their Rydberg energies. And because of that, they're also called, for example, giant atoms. In one of the first experiments on the Rydberg atom arrays, which was particularly in a 1D Rydberg atom array, they saw these robust oscillations. Okay, so they were persisting in time, and that is remarkable because this is a non-integrable system, and we typically expect to see thermalization. But anyway, they saw these, and that actually started, I guess, a new whole field of quantum many-body scars, because later it was elucidated, the origin of these oscillations were elucidated in the context of some special quantum many-body states that were embedded in the otherwise chaotic bulk of spectrum. And these states are low entropy, non-chaotic, and ETH, eigenstate thermalization hypothesis, violating many-body states. An important property of them that they are negligible in the thermodynamic limit. Some people will call zero measure for this. And depending on the model, so now there are so many different models and different classes of QMBS in the literature, but depending on the model, they could be equally spaced across the many-body spectrum. And for example, in this Rydberg atom array context, the PXP model, which explains the physics of the Rydberg atom array in the blockade condition, does. So you see here an example basically of the PXP model, the eigenstate occupation numbers with respect to a Z2 state, a Z2 nail state, which shows you the high overlap relative to the other states here. And that means if you initiate your dynamics at the Z2 states, you're going to overlap mostly with those states, and that's going to naturally give rise to some oscillations in the dynamics. So this was the term of quantum many-body scars was coined for this, and you're going to hear more about this in the next talks, in the next talk by Maxime, actually. But quantum many-body scar, as the name implies, goes back to, maybe follows an older concept, quantum scar. So a quantum scar was introduced to us by Rick Heller in 1984. This is an eigenstate from a billiard that was just introduced to us by Mark, actually, the billiard systems. And in this particular case, like a quantum scar is a quantum eigenstate with a high probability density around an unstable periodic orbit, living in the phase space of this model. So by definition, this quantum scars need a phase space, okay? And this, the scarring orbit has to be unstable. And here the stability is really defined in the context of Lyapunov exponent of the trajectory. So if the Lyapunov exponent is finite and positive value, then it's an unstable periodic orbit. And it has to be living in a chaotic phase space. So that is a very well definition, basically. So if you end up initiating a wave packet on this UPO, I'll be saying UPO for unstable periodic orbit in the rest of the talk, okay? If you initiate a wave packet on the UPO, you would actually see the revivals of the state fidelity in time if you look at the fidelity of the time evolved state with respect to the initial state. So even though like quantum many-body scars were typically in the literature, in the community, are seen as the many-body generalization of the quantum scars, whether there is really a connection, it's not clear. Okay, so is there really a connection between these two concepts? So it goes back to basically questioning what is the origin of quantum many-body scars. There are a few works on this, unfortunately not many works, but a few works, and they're all PXP model. And the PXP model doesn't have a semi-classical limit, okay? And this is the reason why some of these remarkable works actually came up with certain effective phase spaces for the PXP model based on the TDVP, time-dependent variational ansatz equations. So, for example, in this, I'm going to highlight only the first two papers in this direction, okay? So the first work, led by Misha here, found, first of all, came up with a two-dimensional effective phase space, okay? And they found an unstable periodic orbit, but it was embedded in a 2D regular chaotic phase space, so it's a non-chaotic phase space. Later, taking this further, a work led by Maxime, actually, they generalized this to actually higher embeddings. They took the phase space to more than 2 dimensions, or 3 dimensions, which basically can actually host chaos right now. And they found mixed phase spaces, as you can see in this Poincare section here. And that's mixed phase spaces are typically expected for physical systems. And I guess even more interestingly, they found that QMBS in their system, in the PXP model, it was associated with a stable periodic orbit in this mixed phase space. So based on this, to date, to our knowledge, that there is no QMBS corresponding to a UPO embedded in a chaotic phase space. And in general, the relation of the QMBS to quantum scars and regular states remains unclear. And we wanted to bring a fresh perspective to this by studying a totally different model, a spinor condensate, a chaotic spinor condensate. Why it's a different model? Because it has all-to-all interactions in the spirit of this conference. So these collective interactions give rise to a well-defined semi-classical limit. It has a mean field limit, which is a semi-classical limit of the system. That means we can actually go ahead and study the phase space and really see the structure of it, and then see whether the classical quantum correspondence is working, okay, by studying the spectral properties. I'm going to just tell you what we found first and then get into the details. First of all, we identify U-postcard eigenstates in the system, and we actually find these things with the Husimi distributions, which I'm going to define. And we also found that this system hosts not just quantum skies based on this U-pose, but also regular states. So regular state here associated with the stable periodic orbits, okay? And very interestingly, the spectral properties of the regular states suggest a link to QMBS rather than the quantum skies. Okay? So I'll get into the details of this now. A spinor condensate, so specifically we're studying a chaotic spinor condensate. I'm going to come to that point how we make this chaotic. But I think in the beginning of the conference, Hossein actually had given an introduction to spinor condensates. That was though a more general definition, and here we're going to be simplifying that, and I'll tell you how. So this is a typical Hamiltonian for a spin-1 spinor condensate. What you should be thinking of is like a gas of spin-1 atoms, okay? There's no lattice structure here. You can see the kinetic energy, the trap potential, but importantly, the interactions. The first interaction is the density-density interactions, and the other interaction comes from the angular momentum, which brings the spin mixing interactions. So this system has actually been studied like for 2 decades or so, and their quantum phase transitions are very interesting. And so we know a lot about them. In particular, for rubidium and sodium species, we have a great simplification coming. And that is what's called single mode approximation. So under this approximation, the spatial profile of atoms with different spins are the same, okay? So that means the factorization of the wave function in terms of the spatial part and the spin part can happen. And you can actually embed like the spatial part into the normalization constant, and that gives you a simple spin Hamiltonian. And it's an all-to-all connected system. With some density interactions and spin mixing interactions. And typically in an experiment, we have also a magnetic field present, which gives rise to linear and quadratic Zeeman terms. So, but this model is integrable, okay? And we want to study a chaotic spinor condensate. We need to break the integrability. So we gave a prescription of how to do this in the lab. So we first need to add 2 rotating fields, in plane fields, okay, and to the spin mixing Hamiltonian, and then we do a change of frame, and under some large magnetic field condition, during some time averaging, we actually end up with this like simple Hamiltonian, which has the green part is the interaction part, and the red part is what we call spin mode mixing term that you can see here. It actually has the spin 0 and spin 1 components, and the spin -1 components. So this is the part that actually breaks the integrability.
Can you say again why C0 disappeared from the equation?
Why C0? Oh, here, basically, already in the beginning of the spinor condensate.
Yes.
Yes, so...
in HS, in the equation of HS.
Specifically, we are focusing on the rubidium and sodium species, which has this property of that C0 is like the very dominant than C1. That means we are actually not considering that part. Yeah.
Even if it's dominant.
Yeah, but basically it creates a separation of energy scales. So the part that becomes important for the physics is really like the part that's the interaction that comes with the C1, basically.
Okay.
Yeah.
Thank you.
Mm-hmm. Okay. So this Hamiltonian basically is good for us because even with a perturbative integrability breaking like p is equal to 0.05, we have a diverging density of states in the middle of the spectrum, as you can see here, and that will help us with the onset of chaos. Okay. So, and from now on up until the very end, I'll stick with these numbers here for this Hamiltonian. Okay. So first, we're going to look at the spectral properties. When we look at the entanglement entropy for the system, and keep in mind this is a gas, so we're actually looking at the particle entanglement entropy. That is the entanglement of a particle to the rest of the ensemble, okay, an atom to the rest of the ensemble. We find two different two different types of states in this system. So also keep in mind that we're looking in the middle of the spectrum, okay? Most of the states are saturating the high entropy here. So these actually show level repulsion. And then there are some states like in this regular fashion here, and they show level bunching when we do the level statistics. And on top of it, when we look at like the eigenstate thermalization hypothesis properties, we see these like high entropy states, ETH is satisfied, both the diagonal and off-diagonal versions. And of course, like for ETH, we need to stick with some sort of observable, and we choose for this as a spin zero atom population, which is the one that's used in experiments, okay? So on top of this, we can look at the dynamics, and if we initiate the dynamics such that such that the eigenstate occupation numbers are actually on this high entropy band, then we see the local observables thermalized to the microcanonical ensemble prediction as expected by ETH. And on top of the, if you look at the fidelity of the time evolved state with respect to the initial state, we don't see any revivals as expected. So we call these sometimes ergodic or chaotic band of states, okay? Now, what happens to the others? If we initiate our dynamics by choosing a good initial state on these regular regions here, then what we see is these green ones here, okay? So what we see is robust oscillations for the local observables, okay? And on top of it, very high fidelity revivals, okay? On top of it, we were curious about the origin of these regular, what we are saying now, regular states, but I'm going to justify the name in a second. The origin goes back to the integrability. So and it basically we can actually make this observation that when the regular states occur, when they form, there is a certain condition. So that condition is that the number of spins with the number of spins with the +1 is actually higher than the number of spins with the -1. So this condition here that you can see, the opposite is also true too. Okay, so this gives rise to one of these modes to become like a spectator mode. So then we can actually go ahead and replace this operator with its eigenvalue. And this takes our 3-mode Hamiltonian to a 2-mode Hamiltonian. Now this is an integrable model, okay? So then we can diagonalize this, and we can see how the eigenstate expectation values match with our original Hamiltonian. So original Hamiltonian expectation values are these blue dots, and then these red circles are these integrable models eigenstate expectation values. So you can see it actually explains. You can ask me later if you're interested what these other pluses are. But let me very quickly tell you, if you start from now this integrable model here and write it in a spin basis and then linearize this spin Hamiltonian, you can actually write down an approximate spectrum generating algebra for this system. That means like basically we have two specific operators that can take us either up to the tower or between the towers. So specifically up to the tower, this K1 operator, we stay in the same n-1 block, but exchange excitations in this 2-mode effective system, okay? So that means if you know the state here, and if you apply K1, you can generate the next one, and you can go up to the tower this way. So this is pretty well known in the quantum many-body scar community, because specifically like models like PXP model does actually have this kind of spectrum generating algebra properties. And the K2 here for us, basically it translates between different n- blocks and brings a phase. Okay, so you can find the details of this in the SM of our paper. So the point here is that these regular states originate from the integrability, and they actually have an associated approximate spectrum generating algebra. So as you can see, we checked out so many properties of QMBS. Okay, so these states are low in entropy, they show level bunching, ETH is violated, they give rise to robust oscillations and the higher fidelity, and they even show like spectrum generating algebra. But there is one difference, okay, and that is the fact that their numbers actually scale proportional to the Hilbert space dimension. So here in this model, the Hilbert space is quadratically increasing, the number of these states also quadratically increasing. That is different in the QMBS. The QMBS, the number of the QMBS states are polynomially increasing, while the rest of the Hilbert space is exponentially increasing. That's why we're going to call this regular states. We're going to be conservative and differentiate things, okay? And it's going to be more clear why we're calling this regular states in a second. Okay, so I have this table. We're going to fill this table together. So far, we talked about the properties of the regular states, but we didn't yet talk about what is the phase space signature. We also haven't really talked about quantum scarce states yet. In order to talk about these, we need to do a semi-classical analysis. For this, we're going to write down our states in the coherent state basis and go to the mean field limit. You can see here in this coherent state basis, we have 3 spin components. That means amplitudes for 3 spins and the phases. But then there's an irrelevant phase, and on top of it, there's U1 symmetry here. So that means we can have actually independently 4 variables. These variables are the N0 is the number density for the spin 0 atoms. M is the magnetization density, and then there are 2 relevant phases here, theta and eta, okay? So by writing down the Lagrangian, we can derive the equations of motion, and then it has a 4-dimensional phase space. We need to solve this numerically, basically, at this point, to see the Poincare sections. So this is a Poincare section that we'll be focusing on. Let me just orient you. This is a 4-dimensional phase space, and in every Poincare section that I plot, I always fix the energy. Okay, so that means in a 4-dimensional phase space, you're taking an equal energy manifold. And specifically, I'll be looking at this plane and 0 theta plane, because that is actually the one that actually shows us the physics that we're looking for. Okay, and the first thing that we see is a mixed phase space. And an unstable periodic orbit living in this chaotic region. The color code is the Lyapunov exponent of the trajectories, okay? And on top of it, in the lower section of this Poincare section, we have a regular region with stable periodic orbits. Stable, why? Because the Lyapunov exponent is 0, okay? So now we want to see how this classical physics translates to the spectral properties. I'm going to fix the same energy density in my condensate with 200 atoms, okay? So I can diagonalize this. And at this energy, let's first look at the regular region, this pink one here. So for this, we look at the Husimi distribution of our states. So Husimi distribution, as you can see, is the overlap of my eigenstate with the coherent state basis, okay? So, and on top of it, because I have actually a 4-dimensional phase space, while plotting this N0 on the N0 theta plane, I'm integrating out the other dimensions so that I can actually take into account all of the phase space on this plane cut here, okay? And you can see here already some signature of the stable periodic orbits, okay? So basically, regular states are associated with the stable periodic orbits according to this numerical evidence. On top of it, okay, so maybe I'm putting this bit of information now on the table, okay, so, and let's move on with like seeing, okay, great. Let's now move on seeing what happens if we're in this, the high entropy band, if we're taking a state from the high entropy band, and that's exactly where we see a quantum scar coming, okay? So that means a state that is scarred by a U-pop. And consistently with this, if you look at the fidelity, we see a robust fidelity, a robust first revival in the fidelity. And by robust, what I mean is if we increase the atom number of the condensate all the way to 1,000, it will still stay here, okay? So, all right, so basically now we can fill the rest of it. So we found that quantum scar states, they were embedded in the high entropy region, okay? They satisfy this, the entire ensemble of these states satisfy ETH, and it showed Wigner-Dyson statistics. On top of it, there was a robust first revival in dynamics, and then there are some oscillatory observable dynamics that I didn't show, but it decays quickly, again, consistently with the fact that ETH is satisfied, okay? So I'm going to pass this, but you can ask me what happens if we increase P, okay? The integrability breaking term And maybe let me just quickly say that this is not just an isolated UPO. There is a family of UPOs. That means there is a UPO at every energy here. And that actually gives rise to a high scattering of these states. Okay. Just to recap, so we found chaotic spinor condensate could host unstable periodic orbits, which give rise to quantum scars. These condensates can also host periodic orbits, stable periodic orbits, which gives rise to regular states. And that's the naming, right, the regular states come from. Regular and scar states are not only distinct in their phase space, of course, because that's where the definition comes from, but their spectral properties are very different too. Okay, and spectral properties of UPO scar eigenstates are very different than the criteria of QMBS. Instead, regular states are actually reminiscent of the QMBS. So based on this, there were different questions coming up. Let me very quickly tell you what we're up to now. So we wanted to actually see whether there could be a many-body generalization of quantum scars based on this. So what we did, what we're doing right now is we take this all-to-all interacting system and making the interactions finite. They can, of course, give rise to like long-range interactions and short-range interactions. For now, we just stick with the nearest neighbor limit, which basically takes our system to a chain of spin-1 atoms, okay? And in this particular case, we see if we fix this integrability breaking term to 0.5, but of course, let me note that this is not just the integrability breaking term now, it is just transverse field in the chain. We find an entanglement, the volume law, entanglement entropy for this system. Eigenstate expectation values show the ETH is actually satisfied. However, like when we take certain states from here that you see two of them, okay, here on these like spheres, we still see when we look at the Husimi distributions with respect to a many-body coherent states, we see basically some scarring properties, and those are matching with the unstable periodic orbits. So let me just note that how we're constructing this. So before we were sticking with the coherent states, right? We're still sticking with it, but in this particular case, it is the tensor product of coherent states at each site. So I call this many-body coherent state. Let me just wrap up by saying that if you look at the eigenstate occupation numbers for this for a state on the UPO, okay, you can actually see these kind of tower structures coming up, very reminiscent of the QMBS that we know of, and that also gives rise to stable oscillations in the local observables, and that's checked with respect to the ITBD, infinite TEBD method, and they don't disappear basically in the thermodynamic limit. And most importantly, this frequency of the oscillations here match with the UPO frequency. So we think that this is a way to generalize quantum scars, single particle quantum scars to many-body realm, and we're calling this now chaotic QMBS, not to be confused, okay? And the chaotic here means like, you know, with respect to the phase space and the chaotic phase space. So if you have any questions about this part of it, maybe just call this as a chaotic QMBS while call the, you know, the QMBS that we know as QMBS for now. So we're still trying to figure out the classification here, and this will be out like in a month or two. All right, so I'd like to thank my collaborators, Bertrand, Andrea, and Simos. And if you have any questions, just shoot me an email. Yeah, thank you.
Thank you. Question.
Thank you, Ceren, for the very nice talk. I have a quick question. So, if I understood correctly, the idea, one of the motivations for this work is to have a sort of classical phase space representation in order to then make sure that the classification of your quantum scars is appropriate. Exactly. And then you said at the very beginning that this is not possible for the spin models that were studied in the past, especially for the PXP model.
Not, I guess, all spin models, but PXP model doesn't have a semi-classical limit.
So I was just wondering if the criterion is whether you can or you cannot apply, or you can or you cannot represent your states in terms of coherent spin states in that case. Is that correct? Because For your boson model, of course, I guess these are just usual coherent states. Apart from spin models, you can also introduce spin coherent states, right?
I guess yes, you can probably do that. I mean, the direction that we're now going, like, you know, we took those interactions and made them like finite range interactions that actually did give us like a spin one model, a spin one chain. So, and I didn't say it before, but like in that Hamiltonian there, let me go back. This is a starting Hamiltonian, but okay, we choose the normalization such that the energy is extensive, so the mean field limit is still there. So it is possible to construct this kind of like local many-body systems, spin systems, with like a valid mean field limit. And that's what we're actually using here.
But then what was the obstruction of doing that for the PXP?
As far as I know, the PXP model is like, you know, as it is, doesn't have this kind of mean field limit. But the people, as I said in the beginning of the talk, people actually come up with the TDVP equations, time-dependent variational principle equations, for those, and that gives rise to like effective phase spaces to work with. From those, for example, you can also see like the Poincare sections, etc., as I was showing from Maxim's work in the beginning.
Okay, thank you. We can discuss later.
Yeah,
thank you
sure.
so much.
It's probably related to this question. How do you define this the notion of stability for quantum trajectories? Because if I understand, as far as I understand, it's not even easy to define a Lyapunov exponent in the context of a genuine quantum system. So
the beginning of the talk was an all-to-all interacting system, and because of that collective interactions, it actually reduces to a few body system, so that I have a four-dimensional phase space. As long as I have a phase space like that, I can study the trajectories, the classical dynamics, and I can define like, you know, Lyapunov exponent for those. And
but is it like a sensitivity to the initial quantum state now?
So now, like, you know,
when you say stability,
because of the classical quantum correspondence, we see that physics appearing in the spectral, the structure of the system too. But of course, this is a different story if we are now taking the interactions to finite range and going to a chain. Because now what happens is like, yes, I have like a mean field manifold, it's fine, but that doesn't mean that my quantum states are going to stay on there. They will actually leave. And that's the reason, for example, we do also calculations of leakage, quantum leakage for these now, trying to understand like how much they're staying there. In fact, for these states these results that I show, leakage is actually high, and that's what we're seeing. And that is the reason why eventually like there is an ETH coming up here, and these states are in the high entropy region still. Okay, but still what you see is the early time oscillations match the UPO frequency. So in the early time, we are still seeing the classical quantum correspondence.
So how do you know that this leakage is because of scars and not the breakdown of quantum classical correspondence?
How do I see? Can you repeat again?
How do you deconvolve the fact that this is actually a sign of a quantum many-body scar instead of a breakdown of quantum classical correspondence?
You mean like the
appearance of this leakage?
Appearance of the leakage.
Because it might be just because, you know, it's not a good correspondence anymore. So you're saying all kinds of...
It is true. Yes, indeed. Like the leakage, indeed, it's actually defined with respect to the difference between your quantum trajectory and your manifold. Right, so that is indeed like telling you the classical quantum correspondence is breaking down. But what we're seeing here is the initial first time, early time, we're still seeing the effect. And then it just thermalizes. So of course an interesting like question now is like, can we find this in a region where the leakage is low? Okay, so then that will split. Yeah.
So on this point, I guess the question is what happens if you increase the system size, no? So are you going to find higher oscillations or it's dying out?
You can see ITBD, infinite time evolve block decimation tensor network method. Still, it's the dotted curve on it. It's still there. So basically in the thermodynamic limit.
The result doesn't change from 12 to...
So yeah, basically what we're seeing is there are like, yes, there are a few different system sizes here. So we don't see like an appreciable change there.
Hi, thank you for the talk. I had a question for this last part when you say you don't have a breakdown of the ETH. Could you maybe comment about strong and weak ETH? And also, since your initial state is just a product state, could you not build some kind of projector to it or something like this that would be anomalous when you look at the eigenstate?
So the breakdown of ETH, you mean in the...
No, just like at the very end, when you say you don't have a breakdown of ETH in the last, your chaotic QMBS.
Okay, in the chaotic QMBS, no, we do, yes. So you can see, okay, you can already see the eigenstate expectation values here showing like a very homogeneous, okay? So it's in the spirit of diagonal ETH. So, yeah.
But if you build an operator that looks like your initial state, which could be done in a sum of local observable, should that not be special? Should you not see the eigenstate at the top of the tower be further away from the microcanonical average? It should look like your overlap plot in some way, right?
I didn't understand the question exactly. Maybe we can chat later.
Yeah, sure.
Okay.
Thank you.
Just want to make sure I understand this. So to what extent are your results model independent or model dependent?
Of course, all the things that I'm talking here are coming from model, right? And the fact that, the fact that I'm able to find a UPO in the phase space of my all-to-all system, it is a very model-dependent thing. But the physics underneath, right, like the fact that UPO is actually scurrying my quantum eigenstates, that's very general. And that's actually coming from Rick's, work from 1984 or whatever, the Billards. And there are many other systems, like you can take a Dickey model, you can actually see quantum scars there too. So that physics is general. But here, the fact that, for example, we have a family of UPOs and scurrying very largely, that seems to be a little bit like a nice thing about this model, basically. Yeah.
Thank you.
Yeah.
Thank you very much. In the Dicke model, you can move continuously from the regular dynamics where you have stable periodic orbits to the energy region where you have unstable periodic orbits and you see scars. So I used to think that to define the scar, you ask them to be in the chaotic region.
Yes, exactly.
So, but then you move kind of continuously because you are. It was my impression that you are separating the regular to the unstable in a kind of a very clear line. And my impression is, at least in the Dicke model, it is a very smooth continuum.
It is continuous here too. I only showed you the middle of the spectrum. Okay, so if you look at the entire thing, you will see there are actually regular states at the edges of the spectrum. And indeed, it is not clear cut where this UPOs, family of UPOs starting to appear. What we see is they are embedded in this high entropy region. And it's a very nice thing about this is mixed spectrum, right? There is a mixed phase space and correspondingly there's a mixed spectrum. So.
Other questions? Okay, let me ask one. So in the few body case, why do you need to do the spectrum generating algebra to characterize the state? I mean, isn't that the classical action?
So to us, since they are regular, so first we figured out, they're associated with stable periodic orbits. And later, we also wanted to see this connection to the integrability. And that actually took us to the spectrum generating algebra. The fact that it's very regular, right, it actually kind of already smells like there could be some sort of algebra that can take us from one state to another. That was really the reason why we actually went in this direction. Yeah.
Okay. So if there are no other questions, we can ask Ceren again.
Thank you.